Hey Paco, how's it going?
Well enough.
Well enough. Yeah, yeah. Doing good. How's it going, Freddie?
Yeah, it's going all right. How about you?
Yep, yep. It's going good. It's going good. Uh, we're at trig and precalculus now, third unit, and it's actually going pretty smoothly. Um, compared to exponential, so it's really kind of a relief, honestly. Yeah. How's it going, Manzelos?
Pretty good. But I think in teaching I have an issue recently, but I don't know how to fix it. I think people are less motivated to do stuff. I mean, I have less homeworks. I have less people coming to class.
Mood.
So you're saying they're less motivated at this point in the semester, or just like
Yes.
okay, I see. And you're saying because you have less homeworks that are due in the class?
No, they people give me less. So whenever
Oh,
I have the homework, I usually have homework every week, like a written homework, except for like this web assignment or Alex, and I get less the last few weeks. It might be the spring, right? Or I mean, I have the same issue in my classes, but still, you know.
Yeah.
Hey,
Hello.
how's it going? Well, spring break part 3 takes place this week, so that's very exciting. We get so many spring breaks this year.
Spring broken.
Trying to stay on the sunny side. Yeah. All right. And so yeah, I'm leaning towards maybe I might even record an asynchronous lecture after the Wednesday lecture, and then we can just we'll take off Friday and say that we can do that because of the asynchronous lecture. Yeah, so I think that's probably the plan. Probably we will not meet on Friday, and well, anyway, we're making our way through the Leuven-Tate approach to local class field theory, which I think will also be the this should be the end of our discussion of local class field theory, and then we'll have almost a month, I suppose. I have to look at the calendar and see how long it really is to talk about talk about global class field theory from the Adelic approach. Yeah. So anyway, I think that's where we are. Any questions? All right. Well, it is what it is, this Leuven-Tate stuff, and what it is pretty exciting. I'm still very taken with it. I still think it's kind of strange that I just managed to evade this for the first 20-something years of my mathematical career, but oh well. Okay, so yeah, let's just remember the setup. So we're working over our complete discretely valued field with finite residue field as usual. We chose a uniformizing element, and then f sub pi was the set of one variable formal power series that are of the form have zero constant term whose linear term is pi, and that are congruent modulo pi to just x to the q. Okay. So to every such formal power series, we proved that there's a unique formal group law, capital F sub little f, over the evaluation ring, that complete discrete evaluation ring, which has the property that F acts as an endomorphism of that formal group law. But again, more than that, we get an entire formal R module structure. So in other words, we get a ring homomorphism from same ring R into the endomorphism ring of our special Leuven-Tate formal group, which has various properties. So R sort of acts on the, kind of tangent space, so to speak, as multiplication by x. So the linearization of this is just x itself. And then more importantly, well, equally importantly, the multiplication by the uniformizer is the f that we started out with. Okay. And there were some nice equivariance properties and that sort of thing. But in particular, it followed from our equivariance properties that here we chose two things. First, we chose the uniformizer pi, and then we chose the special one variable power series, lowercase f. But it was easy to show that if you fix pi and switch from lowercase f to lowercase g, then yeah, so we have these maps bracket sub f comma g, which have what they satisfy this very nice kind of equivariance property. Okay, which again, if you want to say it that way, makes the Hom from FF into FG into an end FF, end FG bimodule, which kind of is the right way to say it. And in particular, you have the 1 comma FG has this very nice homomorphic property, which, you know, if you stop and think about what this property is telling you, it is precisely telling you that is not only are little f and little f sub little f and f sub little g isomorphic as formal groups over R, the isomorphism is equivariant with respect to the actions of R that we've defined. I don't have a word for it. The actions of R by endomorphisms, okay, that we've defined on both sides, and so this 1 bracket f sub g is actually an isomorphism of formal R modules from f sub f to f sub g. The point being that therefore we should stop worrying about which little f that we chose. Okay, so that's one kind of independence result, but then we still chose pi, and now the question is, what is the dependence on pi? And there is a certain dependence on pi, right? So we will now show that if we switch from one uniformizer to another, the Lubin-Tate formal R modules that we get need not be isomorphic over R. Again, I won't really show that, but it seems to be what's happening. But they become isomorphic over an unramified extension of R. More precisely, they are going to become isomorphic after we base change from R to R infinity. What is R infinity? We'll wait for it for another line or so. So K infinity is going to be the completion of the maximal unramified extension. So again, we had this kind of discussion before. If you take a infinite algebraic degree extension, infinite degree algebraic extension of a complete discretely valued field, or a complete non-Archimedean field. If it were finite degree, it would have to be complete again. If it has infinite degree, it's very, very unlikely to be complete, maybe never. And so then we have to take the completion again if we want to get something which is complete, which we do. So K infinity is we take this infinite degree algebraic extension, which is Galois, everyone ramified with Galois group Z hat, but then we complete again to get a complete field. So again, this, I mean, depending upon, and then, okay, and so then R, that's still a complete discrete valuation field with residue field, the algebraic closure of FQ. It's unramified in the sense that whatever pi is still a uniformizer in this much larger, in some sense, field. And then otherwise, if you take your discrete, if you take your normalized discrete valuation upstairs and you restrict it down to K, you get on the nose, not just a constant multiple, you actually get the valuation back. Okay. And so then R infinity is again just going to be the valuation ring. And so yeah, so R infinity, if you like these things, with some regret, I never talk about it in my courses. The valuation ring here is the ring of Witt vectors over the algebraically closed field FQ bar. So just put that in your mind somewhere. So there is a way, like, so if you have a perfect field of positive characteristic, there's lots and lots and lots of complete discrete valuation fields that have that field as your residue field. And there's one of them which is kind of the smallest one, there's one of them which is sort of unramified in the absolute sense, in some absolute sense, and that's the ring of Witt vectors, and so that's what's happening here. Okay. We don't need to say it that way, so I won't. Okay, and then, yeah, I think I got this far last time. So show that the Frobenius automorphism which for us is an element of is an automorphism of K on RAM over K. It's the one which upon reduction, upon the isomorphism that you get by reducing modulo, letting it act on the valuation ring and reducing modulo the maximal ideal, that gives you an isomorphism to the absolute Galois group of the residue field. And so it's the one that under that isomorphism just becomes the usual x goes to x to the q Frobenius map. And then you're supposed to show that that has a unique continuous extension to an automorphism of K infinity, which we call sigma. Okay. All right, so R infinity is the valuation ring, U infinity is the unit group. We, again, R infinity is still a complete discretely valued field. The residue field is now algebraically closed, which is like in some sense better than if the residue field were finite. Okay, so R infinity is a pretty great ring. We can, all of our standard number theory 2 stuff applies great to this ring R infinity. So in particular, we have the filtration by the higher unit groups, where the nth unit group is just literally everything that reduces to 1 modulo pi to the n. So it's exactly that. Okay. So here's a lemma. I'm not going to go through the entire proof of this. I do want to point out there seems to be a bit of a gap in Harari's exposition. I don't think, I think you could fill it. I wonder if maybe I'm missing something, but let me go through it. Also, this is not really the main point, because I'm pretty sure that this lemma is going to be used in the proof of the lemma that I will state to you next, and I'm not going to prove the lemma that I state to you next. So we're not going to specifically need this lemma, but it's kind of a nice sort of thing. So let's go for the statement first. So first of all, I can solve the equation for any element in the valuation ring. The equation sigma x minus x equals c has a solution. Okay, so that's something that kind of, I don't know, it's sort of looks like it looks like some kind of upstairs lift of an Artin-Schreier type equation, sort of. Okay, so that's kind of what it is. So that equation has a solution. Similarly, this is like the part B is the multiplicative analog of part A. If instead of an element of the additive group of the valuation ring, we have an element of the unit group, then the multiplicative version of that equation also has a solution. Okay, and then the last part, which is kind of interesting, the fixed points, the only fixed points in R infinity of this automorphism sigma are the ones in R. So that's kind of interesting, because that's saying that like K infinity over K, if I didn't complete, well, that's how Galois theory works, right? So K infinity over K is a algebraic Galois extension whose Galois group is topologically generated by this element sigma. That's exactly how it works. So just by regular old, well, pretty regular infinite degree algebraic Galois theory, well, you know, if you have an infinite degree Galois extension, then the fixed field via the Galois group is of course is no larger than the bottom field. And if your Galois group is moreover topologically generated by a single element, then everything which is fixed by that one topological generator, the only things that are fixed are the things that are downstairs. But again, I didn't just take the algebra, I didn't just take K on RAM, I completed it. So you might expect this still to be true. I think I would, but you still have to prove something. Okay, so let me just show you sort of the setup here. Okay, so G again will just be the Galois group of the automorphism group generated by sigma. As in a previous lecture, we have the usual isomorphism, the usual filtration on the unit groups. The first successive quotient is isomorphic to the multiplicative group of the residue field, and the remaining successive quotients are isomorphic to the additive group of the residue field. Okay. This isomorphism literally just being induced by subtracting 1. Okay. And then but these isomorphisms are equivariant for the G action on both sides. Okay, so again, everything except for the equivariance is standard number theory 2 stuff, and we said something very similar in a previous lecture, and I'm just kind of saying the same thing. You can check that you have a very explicit isomorphism here, and you can check that it is just the action of sigma on both sides is compatible with the isomorphism. Okay, so we're going to do this, solve these equations by an inductive process. That's kind of how you expect everything to work when you're working over complete fields, right? So, so the first step here is I'm going to solve this equation modulo the maximal ideal. So find an element x1. I think I'm gonna skip straight to part B, the multiplicative version. So find an x1 in U infinity, so that by bar, again, I just mean reduction modulo the maximal ideal, so that sigma x1 over x1 becomes equal to C after you reduce modulo the maximal ideal. And this is easy because after you reduce modulo the maximal ideal, sigma is just the qth power map. So I'm trying to find an x1 upstairs that once you go modulo the residue field, I'm just trying to find literally just a q minus first root of this element C. And I say, yeah, but my residue field is algebraically closed. So duh, any polynomial equation will have a solution, right? So this equation certainly has, okay, I guess there's going to be, as long as C is meant to be, C is meant to be a unit here, so it's non-zero modulo the, so there's evidently q minus 1 elements downstairs, and you lift them. Okay, so that's the first step. That was fine, certainly, and so therefore you say that the C that you want to, you have your first approximation, so C is equal to so you just divide through here, right, and you say you look at the ratio and you see how you're doing, and the whole point of what we just said is that C does not have to be equal to sigma of x1 divided by x1, but the ratio is now the type of unit that reduces to 1 modulo the maximal ideal. Okay. And then what we're supposed to do is we're supposed to continue this inductive process. I'm supposed to find an x2 so that if I compare multiplicatively sigma of x2 divided by x2 to sigma 1, then it should be in the second higher unit group, which means that it should be congruent. If I take this thing minus 1, it should now be in the square of the maximal ideal, etc. And so Harari just doesn't say anything other than this isomorphism. And I don't know, so I wrote it down just like a little bit. I don't want to fully get into it at the moment. Just sort of show you what's going on. And so if you write all this stuff down, so what does it mean for something to be in the second higher unit group? Again, it means that when you subtract 1, it should be divisible by pi squared. Let's see, right? And so right. So what have I done here? Let me see. Okay, this does not look like the world's most coherent explanation. Let me think for a second. Yeah, maybe I need to write something else. So I'm taking the difference here, and I want it to be in the second unit group. So first of all, it looks, maybe this isn't exactly what I want. It looks like what I want is more like, okay, now I'm just having, let me just write something. So I want, so this looks like more like the equation that I want. This would say that the difference is in the second unit group. Okay, so actually maybe I did make a multiplicative additive mistake, and maybe this is actually easier than what I'm thinking. So this is what I want. And so let me think for a second. And what do I know? I already corrected everything modulo the first power of the unit group. So I know that, let me think for a second here. Actually, let me just think. So, yeah, so I want to find x2. Such that that equation holds. Yeah, so let me just think about this for a second. Maybe this isn't, maybe I wasn't, maybe I was getting the multiplicative and the additive stuff confused now. I now wonder. So let me just think for a second. So I want this to be right. So if I wanted to do this mod pi, that would be no problem. That would be very close to what we already did. So you could certainly do it mod pi, right? So if I take sigma x2 over x2 c inverse minus 1, if I go mod pi, then that's congruent again to x2 to the q minus 1 c inverse minus 1. And so I can certainly make that to be 0 mod pi. Okay, so I find that. And so then what am I saying? So then I'm saying that if I choose such an x2, then I get sigma of x2 over x2 times sigma inverse minus 1 is equal to pi times something else. Okay. And now, right, so now I'm in a situation where I kind of want to divide both sides by pi and sort of try again. So if I take this thing and I divide by pi, so I get 1 over pi sigma x2 over x2 sigma inverse minus 1. So this thing is now still in R infinity. That's what I've done. And now I can reduce this modulo pi, this whole thing modulo pi, and then I want to choose something so that okay, I'm sorry. This is probably not that exciting for you guys, but I think it's probably okay. I think maybe I did a multiplicative to additive mistake that made this thing sound more interesting than it was. But it seems to me that if you just patiently do the algebra and then keep using the fact that every time you reduce mod pi, you're just trying to solve some polynomial equation over an algebraically closed field, so you can always do it. This is maybe looking okay. So let me just stare at this for a second. Well, anyway, let me think more about it. Anyway around, I think you can do this process, and I think you just have to solve the equations carefully. But it looks like it's even hard to see. But it looks like maybe so here I switched between the quotient and the difference, and so I think it looks like I might have confused myself. Let me just think about this for one more second. Yeah, I think you can solve these equations in a straightforward way. So anyway, so sorry, this is not the best exposition. I can come back to it or something if we need to. But I think if you just patiently do this, then you can do it inductively, and you should say something. But I don't think anything terribly exciting happens. So let's just go with the following assertion, which is the next thing that Harari says anyway. I think it's true. I think it's pretty straightforward. So this is the sort of process that we do. So we took C. The first step that I did show you, we wrote C as sigma of x1 over x1, where x1 was actually a unit, I guess. Yeah, times C1. And then I took C1 and I did exactly the same thing. And so I wrote that as sigma of x2 divided by x2 times C2. And of course, you combine those and you get the following. And so altogether, I get C is equal to sigma of something divided by something. It's the same something times an element which is in the next higher unit group. And so you keep doing this. And after the nth step, you write C as sigma of x1 dot 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 xn divided by x1 dot 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 xn times Cn, where xi, you see these xi's are coming into higher and higher unit groups is the idea. And so is Cn. Well, if you're in the nth unit group, if Cn is in the nth unit group, then what does that mean? It literally means that Cn minus 1 is divisible by pi to the n, and therefore Cn minus 1 is converging to n, because the difference between the nth term and 1 has valuation going to infinity. That's what it means to converge. So Cn certainly converges to 1. And then you look here and you say, actually, this infinite product is going to converge as well. In an Archimedean field, infinite sums and infinite products are pretty complicated as to whether they converge. But in a non-Archimedean field, complete non-Archimedean field, just as an infinite sum converges, if and only if its nth term approaches 0, an infinite product converges if and only if its nth term approaches 1. And sure, the xi's, again, are getting they are converging to 1. The difference between xi and 1 is divisible by a larger and larger power of the uniformizer. Okay, so that was kind of the fun part. We construct the element that we want via an infinite product. Okay, so yeah. So again, a little bit of a maybe when I get the chance, I'll just go back and write up the kind of that inductive procedure a little bit more carefully. But I don't think. I just think you just write down a bunch of equations and keep solving them. Okay, right. And so yeah, so an infinite product in a complete discrete valuation field converges if and only if the nth term converges to 1. Unlike these poor people who are trying to do analysis in Archimedean fields, which is much more complicated. Okay, great. And so yeah, so that was part B. That was the multiplicative version of the equation. And so for the additive version of the equation, we're doing, whereas we were using the fact that, well, I don't think I used this fact as well as I could have been. So yeah, something got a little garbled here. I need to go back and do it. So I think the fact that un modulo un plus 1 is isomorphic to the algebraically closed residue field should have been used more strongly in what we did. But okay, let's just agree that we had to do a little bit more there. And then for the additive version, instead of using this, you use this. And then remember, there is a simultaneous generalization. This is actually a general fact in terms of the successive quotients of a filtration that you have from a formal group. Whenever you have a one variable formal group law over a complete discrete valuation field, you can plug in the elements in the maximal ideal, right, to get your group law. You could also plug in the elements of any power of the maximal ideal, and the successive quotients are again going to have the same property. Okay, so those are parts A and B, such as they are. Okay, and now what about part C? So for part C, I'm trying to show that if I have an element in R to the R infinity, the valuation ring, and it's fixed by this extended Frobenius element, then it was actually in K. Okay, so what does this mean? So if sigma of x is equal to x, okay, so that means that once you go modulo the maximal ideal, then I get that x bar to the q is equal to x bar. But again, as we discussed, k is fq here. So again, being equal to the qth power in a field of positive characteristic is a characteristic property of lying in a finite field of order q. So this thing implies that the x bar is in q. And so what does that mean? Sorry, is in fq. Okay. So there exists x1 in R so that the difference lies inside the maximal ideal. Okay, so again, the point is that, I have my R sitting inside my R infinity, and the residue field of R is K, and the residue field of R infinity is K bar. So luckily, this fixed element is actually mapped to not just from an element of R infinity, but is actually mapped to by an element of R. So call it X1. Okay, so I correct by an element of X1, and then I get something which lies in the maximal ideal. So, okay, this is very straightforward. So I take, therefore, x is equal to x1 plus pi times y1, and then you solve this equation for y1, and you get x minus x1 over pi. But x1 and pi were in k, right? And so what does that tell us? Well, if you're in k, then certainly sigma of x is equal to x, right? Because this thing came from extending an automorphism of k on RAM over k, and then little x is fixed by sigma by assumption. So everything on the right-hand side is fixed by sigma, so y1 is fixed by sigma, and so we keep playing the exact same game. Okay, so therefore, doing exactly what I just said with y1 in place of x, I write y1 as something in R plus pi times something else, and I keep going. Okay, and so if I continue in this manner, then I can write x as an element of R plus pi to the n times another element. And again, you look at this equation and you see what's happening as n approaches infinity. Again, this pi to the n times I don't care what is converging to 0 in the topology because it's getting more and more divisible. So Zn converges to x in R infinity. But now, even think about it in terms of metric spaces. So, the metric on R infinity is to find, restricts to the valuation metric on R. And so R and R infinity are both complete. So R is a complete subspace of a complete metric space. Complete subspaces are closed. So R is a closed subspace of R infinity. And so if I can write an element as the limit of a convergent sequence with elements in a closed subspace, that's pretty much what closed means. The limit has to be in the subspace. Okay. So part C was fine. I really wish I'd had the time to go back and fix that thing, but let's just move on. Again, we're probably not going to see why we needed it because now I'm going to state a lemma that I'm not going to prove anyway. The proof of this lemma uses the previous lemma. Okay, so again, there we go. So this is lemma 11.10 from Harari. So I have two different uniformizers. So the second uniformizer will be called omega. Why not? So therefore, omega is equal to some unit times the first uniformizer. That's how uniformizers work. So I'll give myself one formal power series in f pi, give myself another formal power series in f omega. I'm trying to compare the two formal group laws, but this is just a lemma. So by our very first Lubin-Tate proposition, there's going to be a unique one variable formal power series H, whose linear form is ux and is ff equivariant. Okay, that's not part of the assertion yet. We know that already. Then there exists a unit in R infinity and a one variable formal power series whose linear term is epsilon x, and such that sigma of phi is equal to phi composed with h, and sigma phi composed with f is equal to g composed with sigma. Okay, so this is this is like the lemma-iest lemma that you ever saw. It's just not really clear why we're using all these things. The proof is like a 1.5 page calculation, so I'm going to skip the proof. And the only thing that we can do is see how this lemma is being applied. Okay, so let's go to the proposition. We'll see that. We'll just flip back and we'll see how the lemma is applied. So suppose I do have two uniformizers of K, and of course, therefore, they differ multiplicatively by a unit. So it starts out the same. So there's an F and F pi, a G and F omega. Then there exists a unit and a one variable formal power series. Okay, so all this is kind of the same as in the lemma, such that what? Such that, oh, I guess I didn't, if I didn't, maybe I said it briefly. So we have this automorphism of R infinity. Whenever we have a formal power series over R infinity in several variables, we extend the automorphism to the automorphism of formal power series just by applying sigma on every coefficient. Okay, so we can, so applying sigma, we get sigma composed with whatever the multiplication by u is with respect to little f. We also have this, this equivariance. Okay, so this one, of course, is saying that phi is a homomorphism between ff and fg. And then we have this one as well, okay? And you look at this and you say, okay, B and C are saying that phi is an isomorphism of formal R modules, okay? Why is it saying it's an isomorphism? It seems like it's a homomorphism. We talked about that before. For a homomorphism of formal groups to be an isomorphism, it's no big deal. It's necessary and sufficient for its linear coefficient to be a unit in the ring, which it is. Okay, so no problem that this thing is invertible, just the compositional formal power series inverse is going to be the inverse isomorphism. Okay, so yeah, looking at this, it's a little bit unclear what this first condition is doing here, but the second conditions are telling us what we want. So again, what are we saying? We're saying if I have formal group laws obtained from two different uniformizers, we're not saying they're isomorphic over R, but we're saying they're isomorphic over the completion of the maximal unramified extension. Okay, so let's just see how this lemma works, right? So I'm going to apply the preceding lemma with what H? H is just going to be U bracket F. Let's take a look back at what the lemma was. So, right. So in other words, H is the unique formal power series whose linearization is UX, okay, and is UF equivariant. Okay, so we apply that to that proposition. Sorry, we apply the lemma to that power series, and then there is a unit epsilon, and then this other series, formal power series phi, whose linearization is epsilon and satisfies these two equations. Okay. And I think I've just written that down. Okay. So if you take that, so that's the phi, it's epsilon x plus O of 2, yes. Sigma phi should be phi composed with H, yes. Right, and then there's this last one, sigma phi composed with F should be G composed with sigma. So yeah, I believe, yep, so, okay, we can forget about the lemma now because we've just applied the lemma on the nose. Okay, and so if you look at this condition, and just mess with it doing nothing other than ordinary algebra. In other words, if I compose with the inverse of sigma phi on the left to cancel that out, well, that'll cancel it out, and I'll put the inverse of that on the left. And then I compose with phi inverse on the right, that'll cancel that out, and put a phi inverse on the right. That's all I did to get from here to here. I composed with sigma phi inverse on the left, and I composed with phi inverse on the right. So certainly, this just, by pre-calculus, this equation implies that equation. Okay, so now what's going on here? Right, so phi inverse is going to be the formal power series inverse here, and now by definition, I'm going to set G to be what I get by conjugating my formal group law F by phi. And what I want, if you think about it, to say that something phi is a homomorphism between one formal group law and another, it means that if you conjugate by it, in this sense, it takes you from one to the other. So this, having this thing turn out to be FG is exactly what it means for phi composed with FF to be equal to FG composed with phi. Okay, just write that down. Okay, so that's what I want to show. Let's see. So I'm trying to show that this guy is equal to FG. And let's see, I know that, what do I know about G? Well, G is a formal group law over, it's this guy. So it's a formal power series in two variables with coefficients in R infinity. And what do I know about sigma of G? Okay, so I'm just going to do it. Right, so this, I'm not doing anything here. I'm just applying sigma to everything. So here, G is phi composed with FF composed with sigma inverse, where I'm abusing notation. I should really be sigma inverse comma sigma inverse. And so I take, so here, oh, you can't see that. This is too big. Hold on, I need to make this small. Give me a second. Okay, yeah, now I have some room. Yeah, so this is saying that G is equal to what now? So G is equal to phi composed with FF composed with phi inverse. Okay, where that last composition is a standard abuse of notation. Okay, and so if that's true, I'm just going to apply sigma. Just apply sigma to everything in sight. And so that tells me that sigma of G is equal to what I get by applying sigma to everything in sight. And now I just do some simple substitutions and whatnot. So first of all, FF was defined over R. And so therefore, if I apply sigma to coefficient by coefficient and all the coefficients lie in R, then that doesn't do anything. So that's all I did there. And then what am I doing next? So here I'm using the fact that that U bracket F is what you call it? FF is this acts by endomorphism. So if I have an R module and I act on the inside by U and if I have a homomorphism of R modules and I act on the inside by U and on the outside by U inverse, then that gives me the same thing. Anyway, so yes, I'm just using the fact that that U is acting by as an automorphism of this formal power series. That should be, wait, is it? Now I'm getting confused. Hold on. What am I using here? So I know, no, that's wrong. Sorry. So I know that sigma of phi is equal to phi times UF. That's what I did. Sorry. So sigma of phi here I've replaced with phi times UF. Okay. And then what else am I using? I'm using that, what? Oh, if I just take the inverse of that, right? So I just use the sigma of phi is equal to this guy composed with this guy. Well, what about the inverse? Well, the inverse will be the product of the inverses in the reverse order. Okay. So that's what that is. Okay. So just using this identity that it wasn't clear why we cared about it, but now we just used this identity and its inverse. Okay. So that brings us to this line. Okay. Now what? Yeah. So now U is an endomorphism of the formal power series, so I can stick the U on the inside. Yes. Okay. And once I stick it on the inside, it cancels out the U inverse. Great. And so I get phi composed with ff composed with phi inverse, which was G by definition. Good. So, right. Okay, so what did that calculation tell me? That told me that sigma of G is equal to G. So by the last part of the lemma that I actually did prove, right, that means that every coefficient of G actually lies in R, because they're all fixed by sigma. Okay, now we go a little farther. So G, little g composed with capital G, well, capital G was this, okay? And then what else are we using here? We are using this identity that G composed with sigma is sigma of phi composed with F. And so there's a G composed with sigma, G composed with phi. I replace it with sigma of phi composed with F. This is a challenging reading assignment all of a sudden, composed with FF, composed with phi inverse. Okay, now what happens? Again, F is actually bracket U, so it is, you know, you can you can replace them in the other order. That's we can do that. Okay, so we replace those, and then what happens? And then we get what? We use again that phi inverse is equal to this guy times G. Is that what I'm doing? Yeah, if you just look at this equation and you solve this equation for phi inverse, what am I going to get? Wait, is that right? Let me think for a second. Yeah, I'm going to get that. No, I'm sorry. It's just this equation that I wrote down here. I'm sorry. I should have looked at this. I wrote this up actually a few days ago. My mistake was that I prepared too far in advance this time. Okay. So F composed with phi sigma is using this equation, plugging it in here, then I get that. Okay. So, right. So here I've just replaced the F composed with phi inverse with that. Okay, so then I've gotten to this point, and then what's the next exciting thing that happens? Yeah, so this guy is equal to G sigma because FF is equal to FF sigma because FF has coefficients in R. Okay, so that whole thing is G sigma, but I just proved that G has coefficients in R, so that one goes away. All right, so G composed with little g composed with capital G is equal to capital G composed with little g. And so now we go back to our basic prop. I was trying to show that G is equal to FG, and they have the right linear, capital G and F sub little g have the right linearization, and they're both, they both have this, this equivariance property with respect to G, right? So let me think for a second. Yeah, no, that's exactly right. So I'm applying again, the very first proposition from this business, there's a unique, there's going to be a unique form of power series with a given linear form that is equivariant between an F and a G. So I'm applying that with F, little f and little g both being equal to G. And I know that the Lubin-Tate formal group law, capital F sub little g is precisely the guy so that G composed with FG is equal to FG composed with G. That's the endomorphism property. So yeah, so by the proposition that tells us that G is equal to F sub G. Okay, so whatever. It was really just a bunch of straightforward calculations using the lemma. What did we prove? What was G again? G was this guy. So we just proved that this guy was equal to FG, which is great. So what does that prove? That proves that that means that phi is actually a homomorphism between FF and FG. as claimed. All right, this property. So we just proved part B, and then I should also be proving this, and it's very similar. And I'm just going to omit the proof. Okay, so that's the idea. The idea is that you build up a couple of technical results, and then you can prove there is going to be a really a unique, they're not just isomorphic. The isomorphism is fairly canonical. So you see, you take whatever unit gets you from the first uniformizer to the second uniformizer, you're going to get a unique formal power series phi, which is going to give you an isomorphism from the one Lubin-Tate formal group law, capital F sub f, which is based around the uniformizer pi, to the other Lubin-Tate formal group law, capital F sub g, which is based around the uniformizer omega. Okay, so that's the end of that. And so again, our formal group law has no dependence on the choice of little f and has a relatively limited dependence on the choice of uniformizer. Okay. And so now the next, this is the cool part, actually. I think maybe this is my favorite part of the exposition so far. So I'm not going to go. Sorry, I wish I had read over that a little bit and would have gone through it faster. But okay, won't waste more time. So yeah, let me just go for another 10 minutes or so, and I'll start. I want to actually construct these torsion point fields now. So this is where the explicit local class field theory becomes explicit. Basically, the idea is I'm going to prove to you in this, by the time this lecture ends, which was like maybe 4 pages altogether, I will actually give you explicit polynomials whose roots generate a totally ramified abelian extension of K with Galois group, the unit group R star. Okay, so that's what's happening up here. We will now show how to use any Lubin-Tate formal group law to generate an extension K pi over K that is abelian with Galois group isomorphic to the unit group, and it will be totally ramified. Okay. And then the last step is to relate this to the reciprocity map, and thereby show that in particular this is a maximal totally ramified abelian extension. And then again, remember before we broke up the abelian Galois group into 2 parts. There was the unramified extension, which is certainly isomorphic to z hat. Everybody knows that. And then there's a complementary part. Again, the complement is not canonical, and so you see I'm using the uniformizer to choose the complement, but this is giving me a complementary part whose Galois group is R star. Okay. All right, so let's at least get started with this. So the first thing I'm going to do is I'm going to extend scalars to much bigger algebraic extension. K-sep will be a separable algebraic closure of K. So in characteristic 0, just the algebraic closure. In characteristic P, the maximal separable, a maximal separable algebraic extension. Since the evaluation is complete, it will extend uniquely to any algebraic extension. Henselian would even be enough for that. We have more. So by valuation theory as done at the beginning of number theory 2, this valuation extends uniquely to still a rank 1 valuation on K-sep. However, its value group is the rational numbers now, because in particular, if I'm going to a separable closure, then I'm introducing nth roots of my uniformizer. Okay. All right, so so let R-sep be the valuation ring. So again, this is not a discrete valuation ring anymore. It's not even an Noetherian ring. Doesn't matter. Just who cares? It doesn't bother us at all. Just letting you know how it works. It's still a local ring. Every valuation ring is a local ring. M-sep is its maximal ideal. Okay. And so yeah, so R-sep comma M-sep is a great example of a Henselian local ring. This is how you get. This is a great way to get Henselian local rings. You start with a complete local ring and take an algebraic extension, and then take the integral closure. Okay, but again, as I said before, since every finite subset of the maximal separable extension is going to lie in a finite degree extension, okay, you think about this for a little bit, and I say, yeah, if I have any finite subset of M-sep, It lies in the maximal ideal of a finite degree extension. And so as far as plugging in the formal group law goes, the fact that RCEP is not complete is not a problem because it's like locally complete. Any finite number of elements live inside some finite degree, hence complete extension. So go ahead and plug them into your power series. Your power series will still converge. Okay, and so therefore the separable points of the formal group law become an R module. Okay, this I alluded to this before. Now we're doing it for real. This is the most exciting part. Okay, so we get an honest R module, not a formal R module, an actual R module. We call it MF. Set theoretically, MF lives inside the maximal separable extension of K. Okay, but the additive group is different and all that. The R module structure is different. And so now, as for any module over a DVR, I can look at it. I can look at the torsion submodules of it. So by EF super N, I mean just the pi to the N torsion submodule. Okay. I mean, at the moment, it's fine. It's a little bit ambitious. Like, how do I know? Maybe this is a torsion-free R module, and then this is doing nothing. Well, no, that's not what's going to happen. Okay. So we take the pi to the N torsion of our R module, call that EF super N. And then you take the entire torsion subgroup, which is, of course, the direct limit, otherwise known as the union over all the pi to the N torsion, right? Every module structure of modules over a DVR is very simple. So by the way, like we're going to use a fact about the structure of certain infinitely generated modules over a DVR shortly, maybe in the next lecture. Okay, so we have the torsion subgroups. And let K pi to the N be, again, each of these guys is living set theoretically inside K sep. So if I just take the subfield generated by K and by whatever subset of K sep, I don't know what else it is, but it's certainly a separable algebraic extension of K. Okay, so these are my fields. My K pi to the N is what I get by joining the pi to the N torsion points of my formal group law inside the maximal ideal of the separable closure. Okay. So that's my K pi to the N, and then my K pi is I do the same thing with the full guy, and that's just the direct limit of the K pi's, otherwise known as the union. And these are my explicit abelian extensions. That's what's happening. Okay. So exercise. Use our earlier work about independence of uniformizers, or independence from choice of F, rather, to show that these fields only depend upon the uniformizer pi, and they don't depend upon F. Harari just states this, the point being that we know that for instance, MF, this module only depends up to isomorphism on F, because if I switch from little f to some other little g with the same uniformizer, we know that we have isomorphic formal R modules. But again, the field extension that I'm getting is literally adjoining this guy. So just because I adjoin some elements to a field and then I adjoin a different set of elements to a field, just because the second set happens to be isomorphic to the first set as an R module doesn't immediately imply that I'm getting the same field extension. Okay, so there's a little bit, I think you just have to think about this, and if you just kind of, if you write down what an isomorphism of R modules would look like, not even right, or just, what sort of object is an isomorphism of R modules from MF to MG, and then you kind of plug in your field elements, you hit that thing with the isomorphism of R modules, then I think you can use that to see that you're getting the same field. So inside this field, just as soon as you have MF, you also have the image of any element of MF under an isomorphism. That's the sort of thing that you're trying to show. Okay. So there's something to show here, I think. I think if you just calmly write it down, you'll get it, but I wouldn't say it's immediate. Okay, but we're going to use that. Okay. So let's see. Evidently, K pi to the N over K is a separable algebraic extension. Sure, we adjoined a subset of K sep. Because the R module structure is given by power series with R coefficients, the Galois action takes pi to the n torsion points to pi to the n torsion points. So this is a key fact. This is analogous to the fact that, anyway, so this is telling me that this kind of torsion point field is a normal algebraic extension. This is totally analogous to what happens for n torsion points on an abelian variety, right? So because the group law on an abelian variety is given by by regular functions with coefficients in the field k itself, multiplication by n is going to commute with the Galois action. Multiplication by n is therefore going to be defined by functions with coefficients in k. Here, multiplication by pi, hence multiplication by pi to the n, is going to be defined by functions, power series, convergent power series with coefficients in R. And so this is just a good thing to stop and think about and sort of convince yourself that, if you're more comfortable with the same statement on the abelian variety side, then just stop and think about it and realize that it's true for really, really the same reasons. Okay. So just as a Galois endomorph, if I have an abelian variety defined over a field F, right, and I have a point of order n defined over the separable closure of the abelian variety, and then I hit it with an element of the absolute Galois group of the field, I get another point of order n. And the same thing is happening here. Okay. So this tells me that this extension is therefore normal, because one characterization of normal means closed under taking conjugates or taking automorphisms. Closed under the action of the automorphism group of the absolute Galois, closed under action of the absolute Galois group. So it's normal. It was forced to be separable because I just made everything live inside the separable closure. So therefore, each one of these is a Galois extension of k, and therefore each one of these k pi n's is a Galois extension of k, and the k pi is the union of all of them, so that's a Galois extension of k. Okay, so I've constructed my Galois extensions of k. I'm almost out of time. Maybe I'll just state the next lemma here, which is that what is the R module structure of this EFN, right? So again, the EFN literally was the pi to the n torsion on what I got by plugging in the M set points on my formal group law. So it's an R module. What is its pi to the n torsion subgroup? This is what I was advertising in my first motivational lecture, that this is free of it, whatever this thing is, it's a pi to the n torsion module. So it's also an R mod pi to the n module, okay? And in fact, it is a free rank 1 R mod pi to the n module. That's the lemma. And then here, if you just pass to the limit, if you think about this, just if you know this for every n, and then you pass to the limit, then what is the type of torsion R module for which its pi to the n torsion module is free of rank 1 for all n? It has to be this. Okay. But I think this is probably, I think I'd better stop for today because I have, yeah, so we have like 3 more pages in order to get through this, lecture. So I'll do it on Wednesday. But again, this is very satisfying, especially for me. We are, so here we've actually constructed these R modules, and then what's the next thing I'm going to say? The next thing I'm going to say is that the Galois action on this guy respects the R module structure, and therefore the Galois group must be a subgroup of the unit group of this ring, and therefore we're getting abelian Galois extensions, et cetera, et cetera, et cetera. So I'm going to be saying a lot of things which are very, very analogous to the way the cyclotomic character works in the Galois theory of Q, and the way complex multiplication works in the Galois theory of an imaginary quadratic field. It's just going to go over until, and then we get to the point where there's going to be a certain character with values in the unit group of R, and watch how easy it's going to be to prove that this character is just surjective on the nose, and that's going to be the most satisfying part. Okay, so I think we're done for today, unless there are any questions. Okay, so we're still going. So I think it's not going to take I think it's going to take the better part of the next lecture to get through what I just said, not all of it. And then the last section is about the reciprocity. Yes, I think we have maybe 2 more lectures at least on the Lubin-Tate stuff, and we'll see. I may end up, as I said, recording an asynchronous lecture after the live Wednesday lecture, and then we'll see how far that. I think by that point we should be almost done with the Lubin-Tate stuff, but we'll see. Okay, well, thanks for your attention. See you around. Bye.